some noobs! You know, noobs just deserve a good poning sometimes.
It is common to assume that a population will grow at a rate that is proportional to its size. That is, the larger the population, the larger its growth rate. Our problem was to compare two models, Malthusian law, published by Thomas Malthus, and another model published by Raymond Pearl and Lowell Reed. In number one, we had to verify that the equation for P of t was the differential equation from model one. We took the integral and we found that it equaled P of t.
Okay, so for part 2, we had to use the data in table 1 given to us here, which just had the population of all years from 1790 up through 1990, to find a good choice for the constant k, which was in the previous model. So what we did was we took various points in attempts to make best fit lines, and we plugged them into the differential equation and solved for k. So this is our attempt 1 here, and what we did for this one is we used the first point, which was 1790, and the last point 1990. And you can see here that it made this curve here, which was not a very good fit for the data. So after that, we tried again with a second point, attempt 2, which used the point from 1400, which is 1930, rather than the end point, and then we solved the differential equation for that, which gave us this line here, which was still not a very good fit for the data. So, yeah.
Number 4, according to Model 1, what will be the population of this country in 2000 and in 2010? So what we did is we plugged in 210 and 220, which are the corresponding x values for 2000 and 2010, into our equation from Model 2 and solved and got these numbers. Number 5, how well does Model 1 work and why? For Model 1, we used our data from attempt 2 and plotted the data, and this is the residual plot from that data, and it has a clear pattern, which means that the line is not a good fit for the data.
Ugh, disgusting. Let's pwn some noobs!
Okay, so that was all about the first model, or the Malthusian model, and now we're going to be moving on to the second model, published by Raymond Pearl and Lowell Reed. And the main difference you're going to see here is the first model was an exponential model, while this next model goes up and then has a point of inflection and turns concave down and has an asymptote at the top. So you're going to see what that means in a bit.
So in question 6, it asks us to prove that this differential equation satisfies the function p of t. So to start this problem, you would start by separating the variables, so it looks like this. And here we can treat dp as 1, so it turns to this. So next, we'll focus on the left side to simplify it. So first we would want to times it by 1, m over m, so we can simplify the equation to m over p times n minus p. So next is something you'll, like the squishies and the super smart sophomores and freshmen will learn later on. It's called partial equations, I guess. So basically, you could just divide the equation up, and I won't go that much into the details, but it's basically what you do. So after using partial equations, you get, so we can now say that m of p times n minus p is equal to 1 of p plus 1 over n minus p. So that's basically the left side of the equation that we just simplified. So then now going back to the original equation, we would want to take the antiderivative of both parts to solve for p. And as you can see, if we take it, it's much easier. It turns into natural log of p and minus natural log of m of p. And then you simplify that more and you get m minus p over p equals a times e to the negative. Alright, so now by simplifying it more, we can solve for p, which is p equals m over 1 plus a e to negative kt, which is the standard logistic formula. So now by setting p to p sub o, we can plug in 0 into t, and then it would result to m over 1 plus a, And then once we have that, we can then simplify it more to by multiply 1 plus a to this side, and then simplify it. We get piece of o times 1 plus a equals m. And then further simplifying that, we can get p of o plus p of oa equals m. And then we're going to solve for a, and we find that a equals m minus po over po. And next we would plug it back into the original equation. So by plugging it back to the original equation, we get it to look like this. Now to get rid of piece of o over m minus piece of o over piece of o, we would times it by 1, piece of o over piece of o. And then if you times it by 1, it looks like this. And that, as you can see, that is equal to this. Okay, for question 7, it asks us to show that the original equation is equal to this other equation that Wayne Roberts used. So to get this to equal this, we first take the original equation, and we see that there's a e of a over t at the top. So in the original equation, there's no e at the top. So by multiplying it by e of k over t over e of k over t, it looks like this, and that looks really similar to this equation. So now all we do is just a bit of substituting. So we let e of a over t equal e of k over t, b equals m po, c equals po, and 1 equals m minus po. And once we plug that into the original equation, it looks like the new equation.
Okay, so for part 8, we're gonna match that general equation we just did in part 7 to the actual data, or we're gonna try to. So Pearl and Reed took data beginning at 1780 and then used the data from 1790, 1850, and then they used a different figure from 1910 to get this equation here. And so what we're going to try and do is match that, so see if we can obtain the same equation using the data points and see how well it fits the data. So what we did is, if you remember what Jeff was just doing, he ended up partway through with the general logistic function. So all we did is we took these data points here and used a basic logistic regression line. And we actually did end up with exactly the same equation. We then graphed it versus the data points, and what you can see is it fits very, very, very well up until 1910, which is when they were doing this, at which point the population shoots off while the graph continues to go there. So it fits very well up until a point. Okay, so Pearl and Reed came to the conclusion that the maximum population for our country is 197 million approximately. And then question 9 asks how they got this value and is it correct. So that value is right here when the graph levels off. And the way they got that value is m, or the upper bound of a population, is what's going to happen when time goes to infinity. So all you do is you take the limit using that previous equation as t goes to infinity. So what you see what happens here is that as t goes to infinity, this goes to a really large negative number, e to the negative infinity, which is essentially 0. So then you end up with this number over this one, which equals 197 million approximately, which is what they got, and that's how they got it.
In Mounds View Science Olympiad, we have empirically determined that our success rate is directly proportional to the nubosity of the competition.
Okay, so part 10 tells us that Pearl and Reed identified 1914, which coordinates with x equals 134, as the year in which the U.S. population curve would turn from concave up to concave down. How do you think they got this value, and is it correct? Okay, so ideally we all know how you would try and find a point of inflection. Ideally what we'd want to do is to find the second derivative. So we did that here with the model, the model's right here. And then we took the second derivative of it, and I didn't put all that work because it's an awful lot of gross calculus. But the second derivative is here. So I attempted to graph it and attempt to find the roots, but for some reason, and I honestly don't know why this is, but the function had no roots, so I was ideally unable to do that. So they said, how do you think they came to this conclusion? So because I was not able to use the second derivative or the first derivative, which also had no roots to find it, I resorted to using the plain and simple graph. And the point of the matter is, you can actually very clearly see the inflection point on the graph. So they may have just done it that way by plugging points. So when you look at the graph, you can clearly see that at 134, there's a point of inflection from concave up to concave down, which correlates to 1914. So I think that is how Pearl and Reed got this.
Okay, so for question 11, it asks us to find a graph that satisfies the point from 1910 to 1990. Okay. So first of all, we know that our data is a logistic function. So its formula would be P equals m over 1 plus AE to the negative KT, which is the general logistic formula. So next we ran a logistic regression, just like we did in number 8, to find our curve. So here's our curve. So next, the question asks us to find the maximum population of our graph. So to do that, we took the first derivative of p, and we got this, and then we found where it equals 0, which happens to be the year 2316. And by using a line test, we figured out that it indeed is a maximum because it increases before 2316 and it decreases afterwards. So then the maximum population is at the year 2316. And the maximum population at that time is approximately 797,302,143. And then the next part of our question, it asks us for when the graph changes concavity. And to find that, we have to take the second derivative, which is this nasty little thing. And then so we find where it equals 0, and it happens to equal 0 at the year 2040.361. So then we do another line test, and we find out that there is a inflection point at 2040. And then so then we can conclude that the graph changes concavity at the year 2040.361.
You know, sometimes I just love the smell of pwned noobs in the morning.
Care